Cisco Intent-Based Networking and the Journey to Software-Defined Networks. So Chris is a Cisco Press author with 3 books. He's written many different courses, labs, and white papers, and recently authored a global knowledge custom course on Python programming for Cisco network engineers. So now I will hand it over to Chris.
Great, thank you. Thanks for the introduction and welcome everyone. So the topic today concerns a rather large transformation that's been taking place in the area of networking that gives a lot of benefits that were otherwise not there before. The idea of intent-based networking, software-defined networking, is a real powerful team. First, let's take a little look in the past. What we're seeing here is not as much the intended future, but a statement of the past, the way things have been. When I started my networking career in 1997 with Cisco, this drawing held exactly the same way. And here's the key point. Every network device has 2 key elements. Let's call it a brain and a body. The cute little drawings you can see on the right there. The brain, the control plane. The control plane is always needed by anything routing, switching. There's nothing new to the statement. It's been this way for decades. The data plane is where the packets actually get forwarded. Any router or switch to be functional must do that. Again, nothing new. The statement here is also notice that the control plane and the data plane are always on the same device. It's just been that way forever until now with some new options we'll see with software-defined networking. First, what's the problem with this? Number one, how do we manage each one of these individual devices? Notice we have to do it one at a time. Again, that's the way it's always been. So is that the most efficient possible way to manage the control plane of multiple devices? The industry has kind of said no, and software-defined networking, as you'll see, will provide the solution to that. Okay, next, another factor, and as an analogy, take a look as an example, the laptop in front of you. If you're running Windows or whatever operating system, let's say as an example, you have some applications running on it. And you run a new application and it crashes the operating system. The body killed the brain in my analogy here, and the whole laptop goes down, blue screen of death, you have to reboot. Traditional networking has been the same way. In the event of a fail of a control plane, that device has failed. Again, the idea is they're all connected together. Well, in around 2005, that idea started to change. It began actually in a university environment. One of the key leading innovators was a college student at the time named Martin Casado, getting his master's and PhD at Stanford University, doing some research. He came up with the idea of, why don't we separate the control plane and the data plane of networking devices? Take the brain out of the body, separate them. And when we say here the word hybrid, the concept means, well, maybe part of the brain is taken out, maybe all the brain's taken out. And different vendors and different approaches within Cisco have different ways of doing this. So SDN, software-defined networking, what exactly is that? Analogy, what exactly is cloud computing? Note, there's more than one way to do it. As an analogy, how do we do cloud computing? Note, there's so many answers. That's the point. You can go to Amazon to buy something. You can share your files in Dropbox. We can look up our streets in Google Maps. Many different cloud environments exist, just stating the obvious. Analogy, same in software-defined networking. There's not intended to be just one approach. There can be many. But what many share in common is a master brain. And the brain is always called a controller. A controller is not the router, not the switch, but now the brain of the router and the switch that's been removed from the router and the switch. The idea of a controller could be a virtual machine. It could be a physical server. It has some operating system, typically Linux, but it could have any operating system, and it has key software to be the brain. So what are we seeing here? Take some of the brain out of the device and put it over here. Now the idea is, well, what if the brain fails? The body still lives. In other words, data flowing through does not have to go to the controller. The controller is needed for the configuration, for all the settings, for the intelligence, but the controller is not needed for the actual data flow. And that's an important part of software-defined networking that gives us some resiliency. Imagine, as the analogy, you're in your laptop and you load up a new application and it crashes the operating system, but somehow magically the other applications still work while you have a blue screen of death at the same time. Never even possible in a typical Windows laptop. Well, as an analogy, back over here, that now is reality. The idea of intelligence coming out as the controller is a common element of software-defined networking, gives us a lot of power in resiliency as well. So that controller could be, again, different vendors. Within the world of Cisco, Cisco has specific products which are controllers, and that's a big part of our discussion here as well. So software-defined networking, let's put this another way. Who would give the argument that doing a large amount of move-add changes to networking devices one at a time in the command line is the most efficient possible way to manage a large network? Pause. Crickets. That's the point, right? The industry has stated clearly, as networks get bigger, as more devices are added, the ability to efficiently change configuration in multiple devices continues to get less efficient. More devices, less efficiency. That's a simple reality of a one device at a time approach. So that is changed with the idea of software-defined networking. SDN gives us the benefit of taking the brain, the intelligence, the logic of the network and centralizing it. And of course, when we say centralize it, it does not have to mean one centralized device with a single point of failure. Software-defined networking clearly allows for many options of resiliency. We could have many brains, we might say, many software-defined networking controllers. Next, how does the traffic get forwarded? Well, let's put this another way. Has traffic forwarding always been as brilliant as it could possibly be with a protocol like spanning tree? Spanning tree has done its duty over the years. Reality, it blocks ports, it loses bandwidth. Spanning tree takes away bandwidth. Is that the most efficient possible way? Well, software-defined networking, as you'll see, typically gives alternate to spanning tree and does so in a far more efficient way. Another example, let's say we have VMware, and VMware has a really cool ability to take a virtual machine running on one host, move it to another, while it's running middle of the day. The analogy would be like, I have a server, I need to put it in a truck and drive it to another city, plug it in, I moved it far away. Well, if you put it in a truck, you have an outage. VMware with vMotion lets us do that with no outage, middle of the day. While we're still connecting, servers can move. But vMotion does not change network settings. What if there's a router and a different subnet? So software-defined networking gives a solution to the problem of extending a layer 2 network. So anything that needs a larger layer 2 network, any application, VMware being a big driver, can be a big benefit of this. Next, what network design is considered desirable if we can only add a few devices to it and we hit our upper bound limit? As data centers grow, the whole concept is need to be scalable. And again, software-defined networking, it has that in its essence, the ability to scale up to a higher level for sure. Another factor that is kind of like the magic of software-defined networking are two new categories of protocols, and they're called an underlay and an overlay. Software-defined networking, it's all about an underlay and an overlay. These are names of new types of protocols, and together they're a really powerful team. So we never do the underlay without the overlay, or vice versa. They're a team, they work together. There are different options, but we always use both in software-defined networking. Simple analogy, what is it? An overlay is a protocol that runs higher in the OSI model. Overlay, on top, run over. So an overlay typically runs on UDP, that runs over IP, that runs over Ethernet or whatever transport. The benefit is The overlay is the data plane. The overlay, if it hits a router, can go right over it. So overlays can extend in the same data center or to a different data center. Overlays are not limited to distance in any way. An underlay is lower in the OSI model. Typically, an underlay runs on top of Ethernet. Once again, these are a team. So these team together, usually one overlay and one underlay together, can replace a lot of traditional protocols and remove the inefficiencies and make bandwidth scale very highly, having lots of bandwidth, reliability, ease of change, ability to add and change new applications. These are some of the benefits of software-defined networking. So, as an example, what is a common overlay? Probably the most common is VXLAN. Be sure to say the X, VXLAN, not VLAN. A VLAN, virtual local area network, has never been an overlay, nor can it be. VLANs stop at a router, they're layer 2. An overlay can go over a router, through a firewall, to a different data center. An overlay could have added security to it. An overlay by itself does not have security, but security can be added to it. Example, it's not an IPsec tunnel, but that can be added if security is wanted. The underlay is the control plane, the brain, the intelligence. So VXLAN is a common overlay. An example of a common underlay is BGP with a new modification called EVPN, Ethernet, Virtual Private Network. Modifies BGP to make it a powerful underlay, typically inside a data center. We know that BGP is the foundation of the backbone of the internet. What about not for just finding prefixes on the internet, but for finding MAC addresses of hosts inside a data center? That's an underlay. Another example of an underlay is ISIS, intermediate system. That protocol has been around for quite some time, and it's been brought back to life because it has a lot of flexibility. It can work with routing or switching. So where do I have a router? Where do I have a switch? Those concepts start fading away because they're done logically in software with the underlay and an overlay. Again, it's the team of the two that gives the power, not one or the other, underlay and overlay. Another example of an overlay in Microsoft Hyper-V, as an example, is network virtualization for generic routing encapsulation, NVGRE. A big name, simple concept. It's the data plane, runs higher in the OSI model, and alternate to VXLAN. In terms of trends and directions, VXLAN has the biggest growth trend by far. So if we take a look at where the brain could exist in software-defined networking, let's put that right in the middle here. Here's our brain, the intelligence, some product, a server, a virtual machine, software, an operating system. The controller is not the router, but can be the brains of the router. It's not the switch, but can have the brains of the switch. Next, what you and I do when we work with software-defined networking, we'll sit over here on our Windows or Linux desktop, doesn't matter, and we're going to connect in what's called the northbound interface. So in software-defined networking, the idea of a compass is often used. North, south, east, west. So here's north. Our job, where we live, where networking gets done, is in the northbound interface. And when we connect in, we can do so manually, typically with a web browser, command line if we choose, and the ability to do it automatically. Automatically means we can program it. If you have a task to do once, it can be done over and over again. The concept of automation is integral to the idea of an API, Application Programming Interface. An API is not new to the world of websites and programmers. It's now front and center in the world of software-defined networking and Cisco's approach to the ability to automate. Hey, if you can do a task once, what if we got to do it 100 times? Can't we make that automation a little easier? That's done with an API. Simply put, an API is like a doorway between two pieces of software. Example, Let's say we have a software program and another software program. We want them to talk. An API can do that. It's a common language of communication between software components. Now it's used as the northbound interface with software-defined networking controller. There's many APIs to choose from, but the most common and the biggest growth trend today in networking is REST. In the area of web programming, REST is becoming the standard globally. Representational state transfer, another big acronym for a simple concept. Have you ever taken a web browser and go to a website? All right, how simple? That's REST. REST is the architecture of hypertext transfer protocol on the internet, and it allows programmers to allow automation, changes, configuration, viewing information to be done both manually and then repetitively automatically. So REST is a common API of software-defined networking controller. That's where we live. This is the new skill set. How to get good at SDN? Learn the northbound protocol. Beneath it is the southbound protocol. And you and I don't really do anything down here. This gets done for us. In software-defined networking, we contact the brain, tell it what to do, and it does the rest. So here's another new key concept in the idea of programming as it now applies to networking. It's the difference between imperative and declarative programming. Important words here: imperative, declarative. Imperative means you do a task, you see what you do, it gets done. How simple. That's imperative programming. Example, the command line interface on a router has always been imperative programming. You connect in, config T, interface E0, type in an IP address, nothing new there. You type the IP, you see the IP. What gets done is the IP address and subnet mask. That's imperative programming. Benefit, what you see is what you get. Liability, it doesn't scale. It doesn't allow us to do the task efficiently on a large scale. So software-defined networking is typically declarative programming. Declarative programming means let's declare our intent. Literally, what would we like to do? What job do we need to get done? And let's program that in the northbound interface, and the southbound interface gets done for us. What if there's 100 devices down here? The idea of software-defined networking with a controller, it's going to deal with all that. It's going to allow us to automate into all those points. That's one of the key benefits to it. So again, the whole point is a task that needs to be done over and over again. SDN can give us an enormous amount of benefits for this. Another big trend, not mandatory for SDN, but boy, are they becoming a powerful partner, is a new concept called NFV. Another big acronym for a simple concept. Example, what if we take a router, the way it's been for decades? A router, we buy the hardware, we buy the software. Clearly, they work together. The Cisco iOS works inside the router. The Nexus operating system works inside a Nexus switch. Nothing new there. They're a team. They were always joined at the hip. What if we could separate them? What if we could take the operating system out of the hardware and put it as a virtual machine and run it like a virtual machine on VMware or any valid hypervisor? When we do that, that's NFV. What's the benefit? Well, many of the functions that we do in routing don't need all the hardware of a router. They just need the software. Classic example, a BGP route reflector. There's a lot of large carriers that have a lot of big BGP in their environment, need a route reflector, need lots of them to accomplish the needs of BGP full mesh. Well, if you have to buy a separate router for each one of these, that's a lot of added hardware cost. What if you don't buy the routers and you get the routers? The logic, the intelligence is NFV. Take the software out and put it as a virtual machine. Cisco's now been doing this extensively. Example, in our classroom lab environments, we take well advantage of this. The old way was in a lab environment, you would get perhaps sharing physical hardware. It's typically been that way. But now we can give 10 network devices all to one student, give a whole data center to a student because of NFV, because it's all software. It's virtual machine, but it behaves exactly like the actual device. The command line interface, the ability to do software-defined networking, the ability to automate, the concept's all the same. Weakness of NFV, if a network device is predominantly focused on high packet flow, lots in the data plane, NFV will never specialize in that. But the logic, the intelligence of various network functions, NFV really shines in that. So now a specific. What is an example of Cisco software-defined networking in the data center? And one product wins the day, and that is application-centric infrastructure. ACI is a Cisco product that by definition is software-defined networking with declarative programming in the data center. So to be clear, ACI has nothing to do with the campus network. We'll see another solution for that. ACI is not about WAN connection or IP backbone. That's not its point. ACI is in the data center, software-defined networking. How does it work? Well, ACI must have three key pieces of the puzzle. Got to have a spine, got to have a leaf, got to have the controller, and often more than one of each. These three elements are mandatory for ACI. And built within that, software-defined networking, the ability to automate, is everywhere. Notice how I draw a line here. On the right of the line is traditional network Nexus operating system. On the left is software-defined networking. Yet the hardware can be a Cisco Nexus 9000 product. But if you're going to do ACI here, you do it here, you do it here, etc. You do it or you don't do it. Blending and mixing and matching amongst each individual device alternately, that would make no sense. ACI is a collective brain, a collective whole piece. So again, what's the key theme? How does it work? Well, what you and I will do is we'll sit over here on our Windows or Linux desktop, again, doesn't matter which one, and we'll connect in the northbound interface to the brain. The brain, again, is the APIC, Application Policy Infrastructure Controller. This is a Cisco server or multiple Cisco servers, always hardware, always from Cisco, and the benefit is it does all of the declaration of our intent. So in the northbound interface, we program our goal. What do we want to get done? In essence, we literally create a drawing. I mean, literally a drawing. You can see the drawing. It looks like a drawing. Technically, it's not a Visio drawing, but it sure looks like one that you draw to declare our intent. This drawing states the goal of what to do. After we do the drawing, then the APIC does all the rest. The southbound protocol is called OpFlex, OPFLEX. OpFlex started with Cisco. It is now a standard. It is a southbound software-defined networking protocol. What do you and I do in the southbound protocol? Nothing. What do we configure? Nothing. What do we have to turn on? Nothing. What do we have to optimize? You don't do anything. It's already done. We live in the north. It does the south. And when we want to automate, the RESTful API is on the APIC. We do that in the southbound. So again, what we do not do is connect in the spine and configure it. You don't do that. You can't even do it. There's no need for it. You don't connect to a leaf to configure it. Those days are gone. That's inefficient. That's one device at a time. Why not take advantage of the ability to automate? So ACI, therefore, also allows for a very high level of bandwidth. So let's do an example here. Here's a simple example of just a few pieces in an ACI environment. Spine, leaf, and the APIC, the server down below. This drawing is done from the actual Visio templates Cisco provides, so visually it looks just like the devices in the smaller topology here. So let's say we have computer A, and it needs to go to computer B. What's the bandwidth? Well, if we had something like spanning tree here, the problem is spanning tree would block ports, lose bandwidth. So inside here, this is called the fabric. And the only protocols that run in the fabric are the overlay and the underlay. The overlay is VXLAN, the underlay is ISIS. They're always there. They're a very powerful team. They do all the work together. There's nothing to configure. They fully replace spanning tree. So now, if A wants to go to B, what's the bandwidth? Well, note how I could go this way, and I could go this way. So in ACI, which way do we go? If you notice the symmetry of the spine and leaf topology, which is always done with ACI, that symmetry lets us do equal cost multipathing. You go always, all the time. All right, a silly analogy here, but to illustrate a point. Back in the 1980s, there was a goofy Hollywood movie, Mel Brooks, Spaceballs, starring Rick Moranis, kind of making fun of the Star Wars, Star Trek. It was kind of a goofy, silly comedy trivia question. Rick Moranis, dressed up like a silly-looking Darth Vader, said, "We want to go to the really fast speed in our spaceship." What was the button they pressed to get to that super fast speed? The answer was ludicrous speed. All right, silly analogy, but what's the bandwidth in ACI? Literally, it's ludicrous speed. So if I have traffic going from one device to the next, equal cost multipathing is always there. If you want to make the network bigger, get another spine, plug it in the leaf. And now every one of the connections between the spine and the leaf, the slowest speed is 40 gigabit per second. That's the slowest we can go. The fastest, now standard 100 gigabit per second. Every cable is 100 gig. We always do equal cost multipathing. So what's the bandwidth now? We'll add up every cable. All right, now let's put another cable. All right, let's add 5 spines with 2 cables to the east leaf. That's 10 cables. Literally, that's terabit per second bandwidth. Ludicrous speed. Literally, buy the spine, plug it in, plug in the cable, you're done. It's that simple. SDN takes advantage of all that for the rest of us. So the infrastructure, fault tolerance, resiliency, high bandwidth, it's now effortless. It's built right in. Software-defined networking does all this for us. Next example, what about security? So the old default way, if we step back here, how would we describe, as an example, let's go on the right side of the drawing here. On the right side, let's say we were to plug in a computer A, we plug in computer B, and we ask the question, what does it take to make them talk? I mean, how do we network them? The answer is plug it in, you're done. It's always been that simple. Connectivity, real easy. Problem, that is called a blacklist model, and it's wide open. Great for connectivity, terrible for security. I mean, how does a hacker hack? How does a virus spread? Always based on ease of connectivity. If everything can connect to everything, hackers love you. Criminals thrive. Viruses do their dirty work. So when in doubt, it would make more sense to isolate if we don't need something to talk. ACI is never a blacklist model. It's always a whitelist model. A whitelist model means, by definition, when we plug something in, like here's computer A, Windows Server, Dell, HP, Cisco UCS, whatever we plug in here, if A wants to talk to B, the infrastructure, that's done. But the actual connectivity is denied unless we open it up. So what do you and I do with software-defined networking? We start with total security, and we reduce security to allow the productivity that we need, but nothing else. So over here in our Windows or Linux, when we connect in to that northbound interface, we'll make the change to the whitelist. We declare the intent. Let's declare that A is going to talk to B with TCP port 443. Let's put in our drawing, which we can do manually or automatically. So the whitelist shifts the focus of what networking does. With ACI, security is everywhere. It's not like a side thought. It's not like oh, we bought a security device. Everything, always, is secure everywhere. No connectivity works. Analogy, ACI is like implicit deny everywhere. Whatever we forget, it remembers and blocks. So software-defined networking has inherent security built in with the idea of a whitelist put inside here. So again, ACI is the Cisco SDN solution in the data center. What about outside the data center? A new technology Cisco's come out with is DNA. A little play on words. If you remember your basic biology studies, there's the genius work of Watson and Crick back in the 40s, the deoxyribonucleic acid, DNA in our cells. Well, just a play on words here, that's digital network architecture, Cisco SDN product, declarative programming outside the data center. Side note, this has umbrellaed another product. You may have heard the term APIC-EM, Application Policy Infrastructure Controller Enterprise Module. This was the older initial SDN product outside the data center. The new approach now is it's DNA. DNA is software-defined networking outside the data center. Currently, DNA and its center product remains separate from ACI, so there's separate approaches to SDN. Within the world of Cisco, there's not just one SDN product. Here we're seeing several. So DNA has its brain, the DNA center, and the brain controls our devices. Campus layer switches, WAN routers, wireless devices. All of this can have the intelligence controlled in DNA. What if you have to make a configuration change and we want to automate it? We can use a RESTful interface and program in it to make the change. Again, intent-based networking. What do I intend? I intend that the new applications that are being rolled out by our development teams will have support in the network, be secure, get connectivity, have all the bandwidth they need, have fault-tolerant, resilient networks behind them. That whole concept is brought together with software-defined networking. And again, it's DNA, Cisco DNA Center, typically outside the data center. Okay, next, another big trend in the world of Cisco is the idea of network programmability. I should be clear that trend is in all of networking. Let's make an analogy. How about automation in the world of computers? How long has it been there? Well, in Microsoft, automation has been around in their products for decades. Linux automation, nothing new. VMware automation, been around for a decade. What about in Cisco? Reality, Cisco networking has never really had automation built into the core. So what's needed is a change from just doing everything in the command line to the ability to be able to automate it or program it. Here's just a simple example of a show command on an interface. This is the command line interface, nothing new. But what if we could take the same command line and put it in a language that's both human readable and machine readable? Here's a new trend, human readable and machine readable. Because if it's human readable, you and I can read it with our eyes. If it's machine readable, we can program it and automate it and do the task over and over again. If you can do it once, why can't we do it 100 times? Machine readability gives us the benefit. Reality, the command line interface was never designed to be machine readable. It just wasn't. It was designed for our eyes. You connect in a router, you look at the routing table for our eyes. Show version, how long has the router been up? We see that with our eyes. That's human readable, but never designed to be machine readable. Machine readable gives us the benefit of the program and the automation. This is one example called extensible markup language. The idea is whatever I can do in the command line, you can do in XML. And you can see it and then automate it. An alternate to XML, and probably becoming more popular, is JSON, JavaScript object notation. The idea of JSON is it allows us to automate a lot faster. JSON is an alternate to XML. So we could say in the world of networking, in software-defined networking, the concept here is XML and JSON are kind of doing the same job. They're competitors. But when we use one or the other depends on which product supports it. Cisco ACI, as an example, does XML and JSON exactly the same way. We can choose which one we prefer. It's not even similar, it's exact. REST doesn't compete with JSON, it works with it. They're a powerful team. And to automate all this, the largest trend in our industry is now the use of the Python programming language. We've seen an enormous growth trend in the use of Python to program, to automate networking. What can you do in a router switch? You can now do in Python. This is the powerful programming language that has been brought into the networking world to allow us to automate. Trivia question, how did Python get its name? Actually, it's not about snakes. The answer is 28 years ago, a genius programmer named Guido van Rossum, one man decided he wanted to make his own new programming language. He was a big fan of English comedy club Monty Python, and literally that's where the name comes from, and it's stuck ever since then. Python is a free language. It is all open source. Python is very powerful. It's designed based on the English language. So common words we see in the English language, well, Guido, a Dutch programmer with fond of the English language, took English words, put them into Python. And now what can you do with that? All right, what can you do with a router, a switch, a firewall, software-defined networking? We could automate all that. So Python works with the REST in the northbound interface that will configure something with JSON and or XML. Side note, another alternate to these is a program called YAML. YAML ain't markup language or yet another markup language, depending on which reference you pick. It's an alternate to these, but not currently supported in Cisco products. YAML you'd find in something like Ansible, another Linux product, which can do declarative programming and intent-based programming as well. Okay, next, so the idea is programmers, engineers for networking, we've been kind of different. Times have changed. To get a really good benefit of being able to do efficient, high degrees of changes, there needs to be some way to automate it. Python is not the simplest up front, but it's the most powerful. Example, if you only wanted to change one IP address on one router one time, and that's all our goal is, well, use the command line. Simple. I wouldn't touch a thing here. But what if we got to do that task over and over again? There's far more efficiency to be able to program and to automate it. Python has really grown a lot in popularity. Here's a comparison of these. So analogy, what can you do in a router? Type a show command, like show IP interface brief. That's the command line. You can do the same concept if it's supported in that device with XML, JSON, or YAML. These are just different ways to describe what we can do in data. Goal, human readable and machine readable. The goal is both. In this case here, the human readable portion is pretty easy to see. We're talking about an Ethernet interface, number 0, and we can see that it has a no shutdown. It's been brought up. Simple. Clearly, there's more info to that interface, just not shown in this example. But all the rest of this stuff is the machine readable. All the machine readable stuff, the benefit there is we can automate it. Python can work with any of these points to automate. Again, the theme, you do it once, why can't we do it 100 times over and over again to add more efficiency in what we're doing? Everything in software-defined networking adopts this model. SDN is all embracing this. All right, folks, also, for those interested in further on this, the course that was mentioned initially, this is the one that I've developed, and we've been doing quite a bit of this, Python for Cisco Network Engineers. It's all based on SDN, network function virtualization, ability and the skill set to take the language of Python from, hey, what's a snake, and I've never done anything with that, to actually being able to use this for networking. Now, Python can be used in many other areas, of course. Artificial intelligence, Python is the new language. Quantum computing, Python is the language chosen. Complex mathematics is now being adopted in Python. Web programming, Linux administration, Python is the winner. On and on we go. But in networking, Python has the ability to be able to control and automate anything you do. Analogy, what can you do in networking? Well, you can do the same thing now with Python. That Python also gives the ability to automate the automation with SDN, because Python in the northbound interface, we declare a whole bunch of things we want to do, and then the controller does a whole bunch of those things, adding a lot more power to what we can do and implement with that. For those interested in application-centric infrastructure, the idea is how do we start from the very beginning in configuration, set it up, implement SDN for real inside an actual data center environment, and then actually implement the whitelist, both manually and then how to do it automatically with Python. All right, folks, on that note, we'd be happy to start over with questions in our last 15 minutes here. I'll pause for a moment, and our faithful coordinator here will let me know if there's any questions. Be happy to take any here.
All right. Well, thanks, Chris. So as we go through this, so one I have right now, are there any other APIs that Cisco supports besides REST?
Great question. And that is a yes, but we should put the qualifier, depends on which product. Well, let's back over here. Common other protocols. One is called netconf. So the network configuration protocol is a common standard, but designed as an API just for router switch firewall. Whereas REST is a bit broader. REST has a higher growth trend. Example, in Cisco ACI, you can't do netconf, it's only REST. Netconf is supported on the iOS XE router, iOS XR. Nexus switch, not in ACI mode, can do netconf. Netconf, by definition, insists on working with XML. Netconf does not work with JSON as an example. Whereas, as an analogy, REST here can work with either of these, no problem. Another example, REST conf. REST conf is like, well, the dad was REST and the mom was netconf and they had a kid, and it's called REST conf. It's web-based, but still using the ability to program and automate with netconf. And the next one, big Mr. Google, in its enormous cloud platform, created another example, and this is called gRPC, Google Remote Procedure Call. Cisco has taken this free protocol and supported it just in iOS XR and recently the Nexus operating system, but that's it. But the biggest trend by far is REST in terms of trends and direction. If you want to learn just one API, REST would give you the biggest bang for the buck because it's being supported and implemented so many other places. Good question, thank you. Happy to take the next question.
Okay. Can you explain how Cisco SDN works with other public cloud offerings?
Good question. So if we step back over here, so typically and initially, when Cisco came out with ACI, the idea is ACI in April 2013, when it debuted, started from the same three key concepts we use today in hardware, and that is spine, leaf, and the brain, the APIC. And the entire model of doing software-defined networking for security is all built right in. Then around 3 years ago, Cisco said, let's allow a multi-site, multi-pod approach. Example, we have a data center in New York, another one in Chicago. But I want them to act like it's one giant brain, one giant network. Kind of like I want to buy one Ethernet switch for everything in Chicago and everything in New York and stretch it all the way through Indiana and Ohio. And that's pretty hard to do with hardware, but now you can. That's the multi-site approach. It's all logical, of course. We're connecting over a internet transport, but it acts like it's the same environment. Same ACI, the same whitelist. Then, for those who had the privilege of attending Cisco Live this year in Orlando, a new announcement was made to allow ACI to literally be supported inside public clouds of Amazon Web Service, the Google Cloud, Microsoft Azure. Now the hardware, it's whatever they provide, but the ACI SDN intelligence goes from inside your data center to inside what they offer, like it's all the same thing. It's hybrid cloud networking, and Amazon, Google, and Microsoft have all been eager to support that with Cisco. So the idea is the logic, the intelligence we now do, look at all the power. We sit over here on Windows, and we configure one device here in our northbound interface. Now that APIC, it could configure the whitelist for the Chicago data center and the New York data center and what we have in Amazon's cloud and what you put in Google's cloud. And don't stop there. We can also make the changes right in the Microsoft Azure cloud. Power of change of security gets massive in this northbound interface. And again, that's where Python lives here to our RESTful interface, all in the northbound interface. The power keeps growing. In other words, we're not configuring just the devices in this data center, but also devices in the other data center or any other data center still, and in the public cloud. Good question. Happy to take the next one.
All right. How does SD-WAN and SD access fit within SDN?
Great question. So in software-defined networking, once again, there's not just one way to do things. There's many ways. So let's take software-defined networking as the big, giant umbrella. Analogy, cloud computing is a big umbrella. Many ways to do both. SD-WAN is how to take our concepts of software-defined networking and put them in the wide area network. So we have a lot of branch offices, WAN connections, ISR routers as an example. Well, if we have a whole bunch of those and we need to configure those and we want to automate them, well, that's not the job of ACI because ACI is in the data center. So if we leave the data center, that's where DNA comes in. The DNA center has the ability to do software-defined networking for wide area network connections. Next, what about the campus? So any large group of buildings where our users sit in our campus network, traditionally these have been the campus Catalyst switches. The newer one is the Catalyst 9000 as an example. Well, SD access is where the users are accessing the network. Shouldn't we be able to do that securely and implement changes quickly and efficiently? That's SD access, and that's part of DNA Center. So DNA Center is the big umbrella for those. Again, when we talk about campus or WAN, that's not ACI, but for campus or WAN, that's DNA. Good question. Happy to take the next.
Okay, so I think this will be the last one. So how networking programmability is an alternate to command line?
Good question. Okay, so traditionally, again, if we have many devices in the network and want to configure them, it's all done one at a time. So if you only have one router and one switch at a really small company, well, there's no big deal. You go to the router, do what it needs, go to the switch, do what it needs. We're done. But as networks grow, as there's more devices, we start adding from just those two to the hundreds or thousands or even tens of thousands. How are we able to take our ability to do the same things we've always done, same protocols, but do it more efficiently? That's the idea of network programmability. Programmability means connect to the device, the software-defined network controller or the router, switch, firewall, with a RESTful interface, an API, and then allows us to control or configure that in a way that adds power to what we want to do. We could do it once, we could do it many times. Network programmability needs to really be efficient. The concept of human readable and machine readable. Here's another key skill on this to correlate. In the area of programming, there's a very important term called parsing. Parsing is kind of like I just want to get some of the information I need amongst all the info, right? I got a lot of info here, let's say. I just need what I want. Here's a case study. Customer of mine I worked with, they had the following scenario. About 50 branch offices, and in each of these branch offices, they were experiencing operationally some problems with some CRC errors on some Ethernet interfaces, right? And that could affect some of their applications. And it was somewhat sporadic, so they wanted to quickly know where were these occurring. All right, the old way. Telnet or PuTTY into router 1, show interface E0, look at the CRC errors. Okay, they're incrementing or not incrementing. PuTTY to router 2, repeat, PuTTY to router 3. What if we could do all that and only gather the CRC information? That's what Python could do. So Python can work and look inside the XML or JSON. And while we don't see it in this example, you know if you type show interface brief and look inside there, inside all of the connections, you will find all of the output, I should say, information about the CRC errors, just like anything in here. That CRC is just one example, the cyclic redundancy check concept of Ethernet. All right, so if we can see that, what if we only want that information and we want to parse it, like just give me just this or just this on 100 routers in one Python script and display it less than 1 second. That's the power of programming, because anything you can see anywhere in a show command for configuration. In software-defined networking, if you can do it once, you can read it and gather the information you need. So network programmability is not just about configuration changes, which it does beautifully, but also operationally, troubleshooting, reducing time to gathering information exactly as you need it, as quick as you need it. The catch, it takes a little more time up front. If no one's ever done network programmability, you have to invest a little time to learn it, practice it. Once you get good at it, boy, you save a lot of time later. And it's a very powerful approach to, again, take any task and repeat it over and over again. Let the computers do the work for us. That's the goal. We have to make the computers do the work for us. They don't yet think all on its own entirely. It isn't pure artificial intelligence, our phase here, but we can approach that with the intelligence of what we put in.